Well, students, we just finished up Unit 8, where we were solving special equations. Now we're going to start Unit 9, where you guessed it, we're going to graph special equations. Now, I thought we would start off with a little kind of a preview where I want to show you three functions. Honestly, all three types we're going to be graphing in this chapter. Actually in the reverse order. So if you look at that first equation, 6 minus the square root of x squared minus 4x plus 12, I mean, I don't really expect that you know exactly what that's going to look like. It's going to be a special equation. I'm sorry, it's going to be a special graph. Here, let's take a look with the calculator. I typed it in ahead of time, and I went ahead and graphed it. Now you get like this little, it looks almost like part of a smiley face, right? So, you know, if you add some eyes and a nose, you do have a smiley face, but actually, the truth is you have a semicircle. That's right, this equation, this square root equation, you're going to recognize is actually of the form of a circle. And all circles have a center, which we'll learn is a big part of how this graph came about. So that should be fun, but that's going to be the last thing that we actually look at in this chapter. How about the next equation here? We call that a rational equation. Of course, thank goodness we just got done solving that kind of equation, but now we're going to graph it. Well, same thing. I just graphed it ahead of time, and actually, it's equally important that you look at how I typed it in the calculator. You're going to be using the calculator quite a bit to do this, but definitely you're going to be getting good at using parentheses, because if we don't use parentheses, we're not going to correctly code the numerator and denominator. So we got that guy typed in, and we end up with this interesting looking graph. Now, you would have studied this kind of graph a little bit in Algebra 2 last year, or maybe I should say, did you study this a little bit in Algebra 2? Because it's got some special sort of behaviors. One of the behaviors is this, what appears to be this vertical line right here. Yeah, remember, that is an asymptote, and that has everything to do with the denominator equaling 0. What's that you say? You see another asymptote. Yeah, that's right, there is a horizontal asymptote. What does that have to do with the numerator or denominator? Well, it's a little bit more than just a quick answer, but it does look like that, that the numbers that are in this equation are going to have a direct impact on, again, that horizontal and vertical asymptote. Now, the cool thing is you guys are going to learn how to graph this equation without a calculator eventually. I'll be helping you to find the x and y intercepts, and that will also help you navigate what we call the branches. Yeah, see those curves, those branches of the graph really are the graph, but the asymptotes did a great job kind of, dividing or splitting, splitting up those branches. And so we'll spend a lot of time with them. Well, that's a semicircle and a rational equation, both pretty special. How about this third one right here? Well, I would say that one's pretty special too, but it's actually just an old friend. It's a quadratic equation. So we're going to actually spend the first part of this chapter, honestly, just 2 quick days, today and tomorrow, kind of rehashing a little bit about quadratics, because quadratics, they're just so important, right? They make a big part of mathematics. So that's our topic 9.1. And so what do you see here? Vertex form? Yeah, quadratic can be in vertex form. That's where you kind of have that inside and outside style equation. Remember that the number in front of all this, that a value, is going to have a lot to do with the dilation of your quadratic, of your parabola. And then these numbers on the inside, well, yeah, they basically give you the vertex. So we like vertex form. But you know what? We also like standard form. Standard form is when you've got the A, B's, and C's, and some equations that come in standard form, we could change them to vertex form, but we could also leave them in standard form and eventually come up with the graph. Now, kids, that's going to be our goal. Our goal is to make the graph. So when you're ready, we can slide to the next screen here, where I'm going to try to help you understand what I like to call the 5-point method. You see, there's 5 points on a parabola, or we might say there's 5 significant points, and if we find them, then we've got a parabola. Take a look. You can jot it down. Got the vertex. Remember the h and k? Okay, well, that's usually pretty easy to find if you're in vertex form. If you're not in vertex form, you're in standard form. And if you're in standard form, the opposite would be over 2a. Does that maybe ring any Algebra 2 bells? Ding, ding, ding. So that's another way to get the vertex. But notice that that's going to give you just the x value. How about the y-intercept? That's a popular point. That's always when x equals 0. The x-intercepts, those are popular points too. That's when y equals 0. And I'll help you understand this symmetry point. The truth is there's a lot of symmetry points, but we're going to find a symmetry point that typically is symmetrical with the y-intercept. Now, there's another no calculator component to this entire chapter. So even with quadratics, starting today, we're going to graph these without our calculator. I encourage you to do the same thing. When you're doing the homework tonight, all of them are no calculator friendly. I should say no calculator style problems, except for the application. The application will have a calculator. Ready? When you're ready, we're going to actually graph that first equation. Yeah, it was that first equation that was, I'm sorry, it was the last equation that was in that preview screen. So let's actually use the 5-point method on x squared plus 6x plus 4. Now, if I want to use the vertex, or if I want to get the vertex, I could rewrite this problem in, of course, vertex form. And rewriting in vertex form would be actually a matter of completing the square. Okay, completing the square, as maybe you'll recall, is actually a way to change the style of the equation. Remember, you're going to want to think about half of 6 squared. That, of course, is the number 3 squared. That's the number 9. So if I give it 9, I have to take it away 9, which pretty quickly gets me to a point where I can rewrite this problem as x, the half number, so it's x plus 3, the quantity squared, minus 5. Pretty quick. The problem was meant to be kind of quick to get that vertex form. Now, remember, the vertex is going to have everything to do with these inside and outside numbers. And a lot of times people kind of make a little list off to the side here. So, I mean, I can write -3 and -5 right here. But better yet, I'm gonna put it right here. That's my vertex. Okay, how about the y-intercept? Plug a 0 in for x. Now you can plug a 0 in for x right here. That's going to cause you to do 0 plus 3, which is 3 squared minus 5, which is 9 minus 5. So, you know, you can do that in your head. You can do that without your calculator. But you can also plug 0 back into the standard equation. And, oh yeah, you end up with the last number. So the last number looks like it makes quick work of getting that y-intercept. How about the x-intercepts? Okay, now x-intercepts are when the equation is equal to 0. So I need to get rid of some of this extra writing here. When the equation is equal to 0, that kind of feels a little bit like what we were messing with in the last chapter. Of course, this is kind of an easy example of that. But just so you know, we're on the same page. I'm going to solve this by adding 5 and taking the square root of both sides. Now that's going to get you plus or minus 5. And when you subtract 3 from plus or minus 5, you're going to end up with x equaling -3 plus or minus root 5. Okay, nothing's imaginary there, but it does make for some nice x-intercepts. I would be able to write these sort of as just one ordered pair, but we realize that that really represents 2 x-intercepts, -3 plus and -3 minus root 5. Now at this point, it's typically customary to get a little visual, especially knowing that we are going to be drawing a graph and even knowing that I'm trying to get a symmetry point. So let's get a little visual here. Basically, let's make a sketch because that's going to be the goal of all these problems. Now, -3, -5 is somewhere in this kind of ballpark. I can label it again if I want to. 0, 4, whoa, that's way up here. Okay, 0, 4. Now, even though this is a no calculator problem, and I know I've got these kind of crazy x-intercepts, right now I have the ability to draw a graph that, of course, going back to my original equation, is going to have a positive a value, which is going to open upward. So again, right now, even though I know we haven't drawn too many parabolas lately, I, with pretty good certainty, could draw this graph, knowing that the vertex is, of course, that point down in the middle, and the y-intercept's got to connect at 0, 4. Why did I do that? Well, two things to help you see that the x-intercepts are actually both negative. It turns out that -3 minus root 5, well, of course, that was always going to be negative, but -3 plus root 5, well, I guess that's still a negative number. Yeah, even without my calculator, I can kind of see that that's going to end up on the left side. So what about the symmetry point? Well, remember, there is an axis of symmetry. Now, your axis of symmetry goes through the vertex, so it's technically at -3. But what's most important here is that you see that on the other side of my y-intercept, I have a point of symmetry. As long as you understand that this distance right here is -3, meaning that this distance would be another -3, then with a little visual inspection, I can arrive at -6. Careful, 4. It's still going to be at 4, which is the same as the y-intercept. So my symmetry point is -6, 4. And that's a pretty quick rendition of the 5-point method. Okay, do you think we can, why don't we do another one? Usually we end up doing this, perhaps a little bit together, but maybe a little bit on your own. It is a video, I'm not gonna know, but if you stop the video, but some students like to try to ponder some of this on their own. I'm gonna still help you get started. -x squared plus 6x minus 8. So again, if you're kind of thinking, well, I don't know if I want to do this on my own, can you just show me? Well, I'm going to give you a couple thoughts. You could complete the square, but remember, you can't have a negative, or that, for that matter, you can't have any coefficient. Do I really need to complete the square? No. I could use the opposite of b over 2a. I want to make sure that you know how to use that. That's sometimes just as easy. It's pretty quick way to get the x value of the vertex, of course, if you're in standard form. You know, we need a y value, right? So your y value is going to come from, that's right, it's going to come from plugging in 3. Okay, so if I plug in 3, yes, this would still be a no calculator experiment here. Make sure that you're squaring 3 first. That's going to give you 9. Then the negative sign comes along. Okay, of course, I'm going to get plus 18 and then minus 8. So a little bit of -9 plus 18 minus 8, that should come out to be 1. All right, so I got a vertex at 3, 1. Think you can find some other parts of the 5-point method? How about a y-intercept? Shouldn't have been too hard. Your y-intercept, when you plug a 0 in for x, it's just going to be that last number. How about the x-intercept? You just want to equal 0, right? Now keep in mind that you just spent the whole last chapter, or at least part of the chapter, solving equations like this. You still want to be sort of good. You want to be comfortable with this algebra. I don't know about you, but I don't like this negative sign right here. I'm allowed to multiply both sides by a negative. If you multiply both sides by a negative, it's still equal to 0. Makes it a little simpler to think about that factoring. Okay, it's not meant to be super tricky, but let's make sure we factor it with x minus 4. Oops, x minus 4 and x minus 2. So we get some x-intercepts. Keep in mind that those actually each by themselves represent an ordered pair. Please do not put them together as 4, 2. That'd be silly. What are we trying to do here? We're trying to make a sketch. Okay, so that's kind of my hint that typically students will think about the sketch in order to help them get the symmetry point. You got your vertex, got your y-intercept. You do not need to rewrite these numbers necessarily. Now, do you see the parabola? Right, it's going to open down. Remember, your a value is negative, so we've got a little downward open here. It does make sense that, oh, that's kind of cool. I end up with a perfect parabola using my good notes here, or actually it's notability. Okay, but symmetry point, always across from the y-intercept, always symmetrical with the vertex. So it looks like we get the number 3 again. You know, that's just coincidence that that distance is 3. Of course, that's going to take you all the way out to 6. Your symmetry point. All right, well, it's not too bad. It's not meant to be too bad. You should be pretty comfortable with quadratics. It's a major idea from Algebra 2. We just want to tune that up a little bit. Okay. Now, before we move on, just as a friendly reminder, you certainly could have also used the quadratic formula at this point. We completed the square on the previous example, so keep your options open for solving for the x-intercepts. What I'd like to do now, and it'll be kind of the last thing that we do, but we'll spend just about as much time with it, a little application. Okay, quadratics, honestly, they have some good applications. It's a pretty important type of equation because it's of x squared. Of course, it makes an important graph. It's quadratic. It's a parabola. So when it comes to application, one of those popular ones would be what we would call like projectile motion. Okay, you'll study that more in physics if you haven't already a little bit, but when you throw something in the air, when you hit something, when you launch something, as long as it's not, doesn't have its own power behind it, if you like launch, a ball or a football or just something in the air, it's always going to follow the path of a parabola. So, students kind of get a little concerned about this equation. It's got small numbers, it's got decimals, but here's kind of what I want to try to help you see. It does represent the path of a ball. So, try to be a little bit confident here. It's the path of a ball that's going to be the shape of a parabola that's opening down. I know, you probably need me to show you, but okay, what did I just do there? I drew a parabola opening down, and I didn't just kind of just mark anywhere. I'm trying to mark things. I'm trying to start things that make sense. So this parabola, it's going to open down. It starts at 3. Okay, if you want to get a little sort of more fancy here, you can always draw in the baseball player, the softball player that's doing this. So we're just trying to say that, it kind of makes sense. Okay, so what about question 1? It's already been answered, right? The height of the ball is the y-intercept. So kind of connect the starting height with the y-intercept. So that's going to be 3. How about question 2? How far does the ball travel? Okay, we're talking about this distance right here. Okay, we're talking about an x-intercept. Yeah, all these application problems go back to the 5-point method. So the first one was the y-intercept. The second question is the x-intercept. How do we get x-intercepts? Okay, you got to set the equation equal to 0. Now, if you set this equation equal to 0, okay, you're not going to use factoring, and I doubt you're even going to complete the square. Yeah, you're going to use the quadratic formula. So let's kind of, by the way, this would be a calculator-friendly problem. So I'm using the quadratic form of the opposite of b plus or minus square root of b squared minus 4ac. I'm going to just kind of show you b squared minus 4ac comes out to 10384. And then all over 2a, you can probably see how that would be negative 0064. Okay, if you get something like this, you want to sort of be willing to simplify the square root with your calculator to a couple decimal places is fine. So the square root comes out to 102. I still got my denominator at negative 0064. Okay, so I'm going to add 102. When I add 102, I actually just get 02 divided by that negative 0064. And when I subtract 102, I get negative 202 divided by negative 0064. Okay, again, using a calculator would be fine. I just kind of have some of these numbers to quickly show you. But think about something with me here. This x-intercept right here is going to be negative. Well, for the purpose of this problem, that doesn't really make sense, although technically the parabola would come back to a negative spot. But again, I don't really need to find that. This x-intercept right here, okay, negative divided by negative, well, that's going to be positive. So I feel like that one makes sense. And if you actually divide those numbers, because you're dividing by such a small number, you get this really big number, 315. Well, that seems to make more sense with this horizontal distance. Okay, this is probably in feet. I guess it didn't really say that it was in feet, but pretty good idea that somebody slugged that ball 315 feet. Might be a home run. All right, application. Just trying to connect the 5-point method to an application problem. What's that you say? We didn't do the vertex. Well, no, we didn't, but what kind of question would we be asked if we were trying to find the vertex? Yeah, that's right, it's a maximum. It's a maximum height, so if I really wanted to find that, I could go through the opposite of b over 2a. But we have a different problem that sort of goes with the maximum. It's our last application problem, and quite honestly, it's called typically what it would be called a max-min problem. Again, this application is typically what we call a max-min problem. And again, this is a, how about a minimum? This is a pretty classic quadratic application, okay? This max-min problem involving this animal pen, this fence. Take a look at it, you can jot it down. Sometimes at first glance it seems like you don't have enough information, but that's kind of what makes this a good algebra problem. I don't have too much information, so the best I can do is I can start with essentially an unknown. I don't know this distance, sort of this bottom distance on the pen. So if it's an unknown, I can label it as x. Well, that allows me then to label the next sort of distance here, this other side, as x. How about this side? You still don't know what it is, but you do know that it's going to be the rest of your 200 meters. What do you mean the rest? Well, think about it. You've already used 2x, right? You used 2x from the top and bottom. So this side is going to be 200 minus 2x. Now what I'm actually doing here is creating dimensions of a rectangle. Do you see it? I got a length, I've got a width. I don't care which one you call the length and the width, but I've got a length and a width, and that allows me to create an area formula. Okay, now again, if you read the problem carefully, it's asking for a maximum area. So it seems like it would make sense for me to write a formula for area. And that formula is going to be 200 minus 2x times x. Where's this problem headed? Well, it's headed straight to a quadratic. Okay, if you start to simplify this, you can make your equation be negative 2x squared. I'm going to put that first, and then 200x. Now, this is a good point to kind of stop and think, okay, wait, what are we trying to do? Well, we're trying to get the maximum. Now, students, if I'm trying to get a maximum, we have to make the connection that a maximum, in this case, a maximum area. Here's the interesting thing. The equation is an equation for area. So that means my maximum is going to be a maximum area. But what I want you to realize is that that's going to happen at the vertex. So we get to find the vertex. Yeah. How about the opposite of b over 2a? It's a pretty simple formula. Okay. Here we're going to get, basically 200 over 4, which is 50. Now, it's kind of neat to realize that if x equals 50, we're actually talking about the dimensions of this pen. So, yeah, that means that this equals 50. It also means that this equals 50, or that the entire dimension is 200 minus 100. So I can say that my other dimension is 100. Yeah, my rectangle is a 50 by 100. And of course, the area of that, when multiplied, is 5,000. This thing's in meters, so we can call it meters squared. What's that, you say? We could have plugged back in to the y value, or we could have plugged back in to find the y value. Yeah, absolutely. You could plug back in. Again, you're 50, and when you plug that into the equation, you might have to kind of use your calculator a little bit more. But if I do plug that back in, I want you to see how the y value actually comes out to be our same 5,000. Okay, because honestly, the y value is the same as the area value for this problem. Max-min problem, pretty classic quadratic application. You just have to see how you can make the dimensions of your rectangle turn into the quadratic equation. Okay, now, pretty straightforward lesson. A little bit of homework to check out from the textbook, and we'll jump into the other half of this tomorrow. As you can probably guess, we're going to be writing equations, but if you didn't guess, we're going to write the equation of a quadratic.